Hypothalamus Artificial Intelligence, HI, presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called optimization of logistics operations in ports. Case, Latin American port. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all producers of AI technologies. HI is a company at the forefront of high-performance artificial intelligence. A short publication of this case can be found in the document Optimizing Port Operations to Cope with Shipping Congestion in South American Countries. Published by Informs. The Institute for Operations Research and Management Science of USA. The framework of the optimization of logistics operations in ports model is: a port is made up of multiple terminals of different types, which can have independent or interrelated operations. A terminal is composed of multiple docks. Each dock can be composed of multiple quays. In the docks are located the portico cranes which can attend one or more quays. The limits of the cranes are the outreach, or the crane width, and the crane height, or the aerial draft. For operations, the terminal area can be divided into three large parts: seaside, transport area, and land side. The cranes of the dock are in the coastal area. The transport area supports vehicle movements, cranes, trucks and/or trains. Shipping service is one of the many routes, or itineraries, offered by a shipping line. The standard rule is that one or more boats may participate in a service. For the port, the following data of a service is relevant. Type of arrival: irregular, randomly up every n number of hours. Regular, up to a set time every n number of weeks. Regular services take precedence over irregular ones, and deviation: if the service is regular, the deviation is a probability distribution that indicates the number of hours a service can be advanced or delayed. If the service is irregular, it is a probability distribution that indicates the number of hours between arrivals. Movements: it is a probability distribution that indicates the number of containers, or vehicles, or tons, that are embarked and disembarked per arrival, and minimum productivity required: it is the number of movements per hour that must guarantee the port to the service. The general information required for a ship is: ID of the ship, ID of the service, type of cargo, containers, vehicles, bulk, deadweight tonnage: it is the total weight of the ship, that is, of the cargo that carries plus its construction or design weight. It defines the force that the boat will exert on the dock and the mooring bits. Springs must have sufficient structural capacity to support a certain deadweight tonnage. Length: it is the length of the boat. This feature should be considered when defining the location and berthing space of the vessel on a dock. Sleeve: it is the width of the boat, and it is one of the factors that defines which cranes can attend, or not, to the boat. Draft: it is measured from the waterline to the deepest point of the ship. The depth required by a boat to sail is the draft plus a safety margin of around 1 meter. Aerial draft: it is measured from the waterline to the highest point of the boat. It is another of the characteristics that allows to define whether, or not, the crane can attend to a boat or service. And number of cranes: some container ships, vehicle carriers, have their own cranes for loading and unloading operations. Port logistics operations are described below. Assignment of terminals and services. It has a set of services with established itineraries and arrival patterns. Each service has a fleet of boats with set dimensions. It has a group of terminals with docks and cranes, of known specifications. It seeks to assign ships to the docks of the terminals, in order to minimize the waiting time for services in the year. A service must be assigned to a terminal, but ships of a service can be assigned to different docks within the same terminal, and the maximum and average waiting time, per service, should be identified, and at what times of the week the greatest conflicts occur. Assignment of docks and cranes. It has an assignment of services to terminals, with several annual movements per service. On the other hand, there is a connectivity matrix between services that indicates how many containers are moved between the services. It seeks to assign services to the terminals in order to minimize the number of transfers between the terminals while maintaining a maximum average waiting time over the service time. Container transfers between terminals. Some containers that are disembarked are containers in transit that must be reshipped on other ships to other destinations. Among the shipping lines, there are agreements for a certain number of transit containers to be left by one line at the port and then picked up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which, normally, must be borne by the port. The yards and the hinterland connection are in the landside area. The storage yards are organized into clusters, composed of multiple cells. Piled containers, vertically stacked container groups. Map of cells, horizontal organization, at floor level, of the piled containers. Cells, in a piled containers, each container occupies a cell that is located at a certain height, it is a row. Port container operations. The container transfer operations in the port are transfer between the seaside area to the container yard, using the cranes of the ship and portico cranes. Transfers in the storage area, using yard cranes, and transfer between the container yard to vehicles that transport the containers out of the port, using yard cranes. The considerations to be considered in this process are improving the efficiency of container port operations. Problems: the time a ship is docked should be minimized. Operations between subsystems must be effectively coordinated. Container logistics are highly complex. Congestion increases variability and reduces productivity, and space scarcity does not allow terminals to meet the rapid growth of container traffic. Solution requirements: collect and consolidate the execution information of the different subsystems. Leverage mathematical optimization to address the complexity of interconnected subsystems, and increase terminal performance. Congestion at container terminals. Import and export terminals, yard cranes are a bottleneck. The availability of yard cranes generates congestion, and delays in the loading or unloading program, and high volumes of empty containers lead to congestion. Transfer terminals, yard space is a bottleneck, dock cranes are a bottleneck, and space availability leads to reorganization, congestion and delays in loading or unloading schedule. Then, better coordination between the dock and the yard is critical to smoothing the bottleneck. The bottleneck is shared between several vessels, therefore, a holistic view of the process is necessary. Optimization of loading and unloading operations. Problems: loading and unloading operations on different vessels and cranes generate congestion, and several containers from the same area must be moved to the dock ship at the same time, generates a yard clash. Reducing the yard clash is the key concern. At cluster level, more than X movements in a cluster during a given period generates a yard clash. At stack level, more than X movements in Y consecutive stacks during a given period generates a yard clash. The berth allocation process implies the ship must arrive to the terminal assigned to the service. A key must be assigned to the ship, respecting the restrictions of the key and the ship, and the cranes must be assigned considering the assigned key, the required productivity, and the cranes of the ship that will be used. The interconnectivity of the models used are demand model, forecasting of arrivals embarkations, based on predictive analytics, allocation of terminals and services model, tactical planning optimization model, key allocation model, real-time scheduling model that defines assignment of vessels to keys, assignment of cranes to vessels keys, schedule of services per key, and schedule of services per crane. Assigning services to terminals model. It aims to specifically assign the terminals in which the services will be served. To do this, it makes a simulated assignment of what could happen in the coming months, in the set of terminals. The model is of a tactical type, since it must be used with a frequency of the order of months, according to the demand for services expected for the medium term. It is based on continuous time modeling using a stochastic mixed linear programming (SPMIP) model. Assignment of ships to keys model. Its purpose is to produce the following specific items: the assignment of vessels belonging to shipping services, to a dock that belongs to a terminal, and to a set of cranes that will serve the service. All the above considering the operating restrictions of both, the vessels and each terminal, their docks and the cranes of each dock. A detailed schedule, by hours, of the assignment of boats to docks. This implies defining the assigned dock, the time of entry, waiting, operation, and departure for each vessel. And a detailed schedule of container transfers between terminals, considering the previous vessel arrival schedule. The model is of an operational type. It is run daily or whenever an event, contingency, occurs that merits the rescheduling of the running program. It is based on continuous time modeling by means of a mixed linear programming (MIP) model. The screenshot shows a Gantt chart for key activities. The main characteristics of the project were: challenge, to implement tactical planning and scheduling models to optimize the operations and commercial services of the port. Solution, implementation of a set of optimization models for the definition of operations timetable, and the allocation of ships to docks and cranes to ships, to optimize the management of shipping services, in the two terminals of the port. Result, the mathematical models allow to optimize operations of the port for planning terminal services assignments, planning big events in the port, and analysis of commercial opportunities. The port has two terminals to serve container ships. As an example, the information of the Conticar terminal is presented. It has 4 berths, a minimum separation between boats of approximately 25 meters must be left, and if a ship is found docked at dock SO6, a separation must be left, with respect to the boat at the marginal dock, SO7 SO8. The table presents the available cranes and their characteristics. The table presents a partial summary of the services and vessels used. The table shows the container connectivity matrix between services. All mathematical models share a single data model, making it easy to interconnect models along the decision-making chain. Below are some shell windows containing the tables of the HiPort information system. The screenshot presents an Optex explorer of the elements of the HiPort information system. The shell window contains the master table of terminals, and the tables of relationships between the terminals and ships and keys. The shell window contains the master table of keys, and the tables of relationships between the keys and terminals, cranes, and ships. The shell window contains the master table of ships. The shell window contains the master table of ships, and the tables of relationships between the ships and terminals and keys. Below are some shell windows containing the results tables of the models of HiPort. The screenshot displays an Optex explorer of windows for the output of a model. The selected table points to the variable time of entry of the ship to the dock. The image presents a selection of a pivot table in Excel with the schedule of services per key. The image presents a pivot table with the crane utilization time per service. The image presents a pivot table with the crane utilization time per service. This is a Gantt chart of keys, cranes, and ships. This is a Gantt chart of key SO5 and ships. This is a Gantt chart of key SO6 and ships. This is a Gantt chart of key SO7, SO8 and ships. This is a Gantt chart of keys and cranes. Hypothalamus Artificial Intelligence. The creator of the artificial hypothalamus technologies. Thank you for your attention.